Hello students, this is Professor Chalai, and in this video we're going to look at limiting reactant and theoretical yield. And by the end of this video, you should be able to identify the limiting reagent or reactant and calculate the theoretical yield. As always, you can follow along with our chapter 4 workbook. Now, many of you may have already done the online pivot lab that looked at limiting reactant and theoretical yield. I will also sort of put the video on our lessons for this week. That video is optional. Some of you have watched it last week for Pivot Labs, and some of you will need to watch it this week. So eventually, I guess, all of you will watch it at some point in time. But I would go back and watch that first. It goes through some of the calculations, and then you can come back here, and I'll go through them in a little bit more detail, and so that hopefully you can understand it a little bit better. But let's look at this idea of limiting reactant and limiting reactant, excess reactant, and the theoretical yield. So our textbook uses a very nice example, and I'm going to go with it. And it's the idea of making sandwiches, cheese sandwiches, using bread and cheese. So in making a cheese sandwich, we know that we need 2 slices of bread and 1 slice of cheese. So the ratio would be 2 bread to 1 cheese, right? 2 slices of bread to 1 slices of cheese to make a sandwich. So that means that if, let's say, you had a loaf of bread, which, I don't know, has 25 slices, and you have a pack of cheese that has, I don't know, 8 slices of cheese, how many completed sandwiches can you make? Well, let's figure it out. In this, the ratio is 2 to 1, but once you've used up your 8 slices of cheese with 16 slices of bread, right? The ratio is 2 to 1. Then you've used up all of your hang on, let's write that. You've used up all of your cheese, so it doesn't matter that you have extra bread lying around. It means that you can't make any more sandwiches. So all you'll do is end up with 8 sandwiches, and you'll end up with an extra, what's the difference here? 25 minus 16 is an extra 9 slices of bread that don't go used up. So because you used up all of the slices of cheese, this becomes your limiting reagent. Your bread that still has some left over, right? This is your excess reagent. And this 8 slices of 8 sandwiches that you can make, this is your theoretical yield. In short, your theoretical yield is the amount of product you can form when you've used up all of your limiting reagent. In this, in examples like this, it doesn't matter if you add extra slices of bread, you still can't make any more sandwiches because you've run out of cheese. But if you add extra cheese, if you add extra of the limiting reagent, you can form more product because you have excess reagent lying around. So that's the nitty-gritty of it. So, well, not the nitty-gritty, but that's a broad overview of what a limiting reagent, an excess reagent, and theoretical yield is. So let's just do some formal definitions. So your limiting reagent is just the reagent or reactant that gets used up in a chemical reaction. Your excess reagent is the reagent left over in a chemical reaction, or that doesn't get used up. And then finally, the theoretical yield is the amount of product, and usually it's referring to the most useful product if you have more than one types of products. So it's the amount of product formed from all of the limiting reagent. And usually you'll calculate this calculated from stoichiometry. And that's why it's called theoretical yield. It's if theoretically, if you used up all of your limiting reagent, you've how much product can you have, and you'll figure that out through calculation. Let's look at some examples. Let's look at number 24. We have a reaction between methane, oxygen, and oxygen to form carbon dioxide and water. This is a typical combustion of methane to form carbon dioxide and water. So in this reaction, let's say we've mixed 30.0 grams of methane and 33 grams of oxygen. Which one is the limiting reagent between your methane and your oxygen? Which one gets used up first? And based off of that, what is your theoretical yield? So the way I usually handle this, and if you've done the pivot lab and looked at those examples before, you'll see how I did those. But I will try to figure out what's my yield with each of these. If I start with methane, how many product can I get? If I start with oxygen, how much product can I get? Whichever one forms the smaller amount of product, that's my limiting reagent, and that will be my theoretical yield. For example, let's look at our making our sliced bread. If I only looked at my bread, I could have formed 25 divided by 2, or around 12 and a half, really 12 sandwiches. So if I used up as much as much of the slices of bread as possible, I'll be able to form about 12 sandwiches. But if I looked at my cheese, I realized that I could only form 8 sandwiches, right? Because we need 1 cheese per each sandwich. So because our cheese lets us form the fewer amount of product, that's how we figured out it was the limiting reagent. So let's do the same thing. We'll start with each of our reactants, figure out how much product we can form, and whichever one forms a smaller amount of product, that one will be our limiting reagent. So let's go with methane. Let's start with methane, CH4. Let's see how much product we can form with methane. Well, we're starting with 30.0 grams of methane. And this is going to be a stoichiometry calculation where we're starting with methane and we need to figure out how much product we can form. In this case, we have 2 products. Let's pick the carbon dioxide as the interesting product because water is usually found everywhere. So let's just use carbon dioxide as the interesting product. So if we start with 30.0 grams of methane, how much grams of carbon dioxide will be able to form? Well, first, this is a stoichiometry calculation, so we need to figure out how many moles of methane that we have. So the molar mass of methane is equal to the molar mass of carbon plus 4 times the molar mass of hydrogen, which gives us, where are we? 16.05, there we go, grams per mole. So let's just put the labels. So we start with 30.0 grams of methane. We can convert that to moles of methane using the molar mass. So grams of methane to moles of methane. And then we can convert from moles of methane to moles of carbon dioxide using the mole ratio. And according to this equation, 1 mole of methane goes to form 1 mole of carbon dioxide. So 1 mole of methane forms 1 mole of CO2. So moles of methane cancel out. And now we just need to convert CO2 to mass. So let's calculate the molar mass of CO2. It's 12.01 for the carbon, 2 times 16.00 grams per mole for the oxygen. And so that gives us a molar mass of 44.01 grams per mole. So 44.01 grams of carbon dioxide per mole of carbon dioxide. So here we'll get moles of grams of carbon dioxide as our answer. Let's use red. so grams CO2, and we plug all of these into our calculation, and we'll see that we get 82.3 grams. So let's just circle that. All right, so now that we've used, let's clear some space here. Now that we've used the methane, let's look at the oxygen. Let's see how much product we can form if we start with our oxygen. So oxygen, let's do our stoichiometry calculation. We start with 33.0 grams of oxygen. The molar mass of oxygen, so that we can convert from the mass of oxygen to the moles of oxygen, is 32.00 grams of oxygen per mole of oxygen. Remember, this is just 2 times 16, so that's how we get the 32. So that cancels out. Now we can convert from moles of oxygen to moles of carbon dioxide. In our mole ratio here, for every 2 moles of oxygen, there's 1 mole of carbon dioxide. So let's do that. 2 moles of oxygen for 1 mole of carbon dioxide. And now we can convert to mass of carbon dioxide, which is our product. So we use the molar mass of carbon dioxide, which we already calculated. There we go. And so if we plug all of these into our calculator, we get a number that is 22.7 grams of CO2. Let's circle that. So we have 2 values of 2 possible products. If we used up all of the methane, we'll get 82.3 grams of carbon dioxide. And if we started with the oxygen, we'll get 22.7 grams of carbon dioxide. So because oxygen forms the fewer amount of product, or lesser amount of product, that is our limiting reagent. So let's write that. So the limiting reagent, the one that gets used up first, is going to be oxygen. The theoretical yield is the amount of oxygen, amount of carbon dioxide. Theoretical yield is the amount of carbon dioxide that the oxygen will form when it gets used up, which is 22.7 grams. So there we have it, the theoretical yield and limiting reagent calculation. Now that you have some practice with that, try numbers 25 and 26 on your own. Pause the video, try them out, and when you unpause, I'll work them out with you. Okay, let's look at number 25. We have magnesium and oxygen to form magnesium oxide, and we start with 36.9 grams of magnesium and 29.0 grams of oxygen. Again, what's the limiting reagent and the theoretical yield? Let's start with our magnesium. So for magnesium, we have 36.9 grams of magnesium. To convert to number of moles, we use the molar mass of magnesium, which is, if you look at our periodic table, 24.31 grams of magnesium per mole of magnesium. So grams of magnesium cancel out. Now we're going to use our mole ratio to convert from moles of magnesium to moles of magnesium oxide. And we see that we have, for every 2 moles of magnesium, we have 2 moles of magnesium oxide. And then now we're going to convert to mass of magnesium oxide. So the molar mass of magnesium oxide is equal to the molar mass of magnesium, which is 24.31, plus the molar mass of oxygen, which is 16.00. And so that gives us, there we go, that gives us a molar mass of 40.31 grams per mole. So let's use that. 40.31 grams of magnesium oxide per mole of magnesium oxide. We punch all of this into a calculator, and we will get 61.2 grams of magnesium oxide. Let's just circle that. We'll come back to it later. Now I'm going to create some space to try the second reagent, which is starting from oxygen. So let's do that. Starting with oxygen, we have 29.0 grams of oxygen. We divide by the molar mass of oxygen, which is 32.00 grams of oxygen per mole of oxygen. We convert that from moles of oxygen to moles of magnesium, and from this equation we see that for every 1 mole of oxygen we have 2 moles of magnesium oxide. So 1 mole of oxygen per 2 moles of magnesium oxide. And then finally, we convert again to grams of magnesium oxide using the molar mass of magnesium oxide. Punch these numbers into our calculator, and we will get 73.1 grams of magnesium oxide. So, which one forms the lesser amount of product? It is, of course, the magnesium. So, if we're going to write this out, our limiting reagent is magnesium. And let's use a different color. Or theoretical yield is 61, right? 61.2 grams of magnesium oxide. There we go. All right, if you haven't tried number 26 yet, it's a long one. So pause the video and try it now. Otherwise, I'm going to work it out for you. Okay, let's look at part A. Write a balanced molecular equation for this reaction. So we're starting with magnesium nitrate. So let's write that, magnesium nitrate, aqueous. We have sodium carbonate, so plus sodium carbonate, aqueous, going to form what? Well, let's figure that out. So magnesium we know has a charge of 2 plus, carbonate has a charge of 2 minus. So when we form our product of magnesium carbonate, when we switch their ion, it's magnesium carbonate. We just need one of each to balance it out. And what is is magnesium carbonate soluble or insoluble? If you look at our, if you've memorized or look at our solubility chart, we'll see that carbonates are insoluble. Magnesium is not an exception, so that's going to be solid. The other ionic product, when we exchange the ions, is going to be sodium and nitrate. Sodium has a charge of +1, nitrate has a charge of -1, so that's just going to be NaNO3, and that's going to be aqueous because also sodium salts are aqueous, all nitrates are aqueous, so that's all good. Now let's look at balancing. We have 1 magnesium on the left, 1 magnesium on the right, that's okay. We have 2 nitrates on the left, but only 1 on the right, so let's make that a 2. That means we now have 2 sodiums on the right. We have 2 sodiums on the left, that's okay. We have 1 carbonate on the left, 1 carbonate on the right, that's okay. So this is all balanced. All we needed to do was put a 2 right there. All right, let's look at the complete and net ionic equations. So magnesium nitrate breaks apart because it's aqueous to magnesium 2 plus aqueous. You always need to write the aqueous sign, and 2 times the nitrate, then NO3 minus aqueous. If you hear, I'm sorry, if you hear a lawnmower in the background, it's just my neighbor mowing his lawn. Okay, now we have sodium carbonate that breaks into 2 sodium ions, which is just a +1 charge, aqueous, plus a carbonate, which is CO3 2 minus charge, aqueous. On the product side, we have magnesium carbonate, which is solid, so that stays together. Let's use this color, magnesium carbonate, stays as a solid. And then we have 2 sodiums, right? Because this is aqueous, it breaks apart. So we have 2 sodium plus, aqueous, and we have 2 nitrates, aqueous. So this is the complete ionic equation, and you should label it so that you know what it is. So it's complete ionic equation. All right, let's look at the net ionic equation. We just need to cancel all of the things that are the same on both sides. So we have 2 sodiums on the left and the right. We have 2 nitrates on the left and the right. So for the net ionic equation, what we just have is a magnesium 2 plus aqueous plus a carbonate 2 minus aqueous, going to give us our magnesium carbonate solid. All right, let's look at the limiting reagent and theoretical yield. So we start with some amount of magnesium nitrate and some amount of sodium carbonate. So let me highlight that. Some amount magnesium nitrate and some amount of sodium carbonate. The only difference here is these are in volume and concentration rather than mass. But it's no different. Like, we know how to go from mass to moles using molar mass, but we also know how to go from volume and concentration to moles using molarity. So let's do that. So let's start with our magnesium nitrate. That's a good place to start. Magnesium nitrate. We start with 10.00 mils. We know that we can convert to number of moles using our molarity, right, which is moles over liter. So we need to first convert our volume to liters. So that'll be 1,000 milliliters, 1 liter. There we go. Okay. Now we can convert to number of moles using the molarity, which is 0.01 moles over liter. So liters cancel out. So now that we have moles of magnesium nitrate, so we should write magnesium nitrate so we remember what we're working with, we can use our balanced chemical equation to convert from moles of magnesium nitrate to moles of our interesting product, which is our precipitate magnesium carbonate. It's solid, and so this is the precipitate, PPT. Okay, so let's look at our balanced chemical equation. For every 1 mole of magnesium nitrate, there's going to be 1 mole of magnesium carbonate. So 1 mole magnesium nitrate for 1 mole of magnesium carbonate. So moles of magnesium nitrate cancel out. Now that we know the moles of magnesium carbonate, we can convert to the mass, because that's going to be our theoretical yield for the next part of the question. So let's do that. The molar mass of magnesium carbonate is equal to the let's see, it's 84.32 grams per mole. If you did the calculation, I'm not showing the work here. All right, so that we multiply by 84.32 grams of magnesium carbonate over moles of magnesium carbonate. And if we plug all of these into our calculator, we should get 0.08 grams of magnesium carbonate. I'll circle that. I'll come back to it later. So that's the first reagent, magnesium nitrate. When we start with magnesium nitrate, we'll end up with 0.08 grams of magnesium carbonate. Note that I use 1 sig fig because our concentration, 0.01 moles per liter, is 1 sig fig. All right, let's start with our other reagent, see what we get. So let's put a nice little line there so I can work under it. Let's look at our sodium carbonate. So if we start with sodium carbonate, we're starting with 8.00 mils. We can convert to number of moles using molarity, but first we got to convert to liters. So there we go. Now we can multiply by the molarity, which is 0.02 molars. So 0.02 moles of sodium carbonate over liters. So liters cancel out. Then we use the mole ratio, right, to convert from sodium carbonate, our reactant, to our interesting product. And our reactant, the ratio here is 1 mole of sodium carbonate to 1 mole of magnesium carbonate. So let's do that. There we go. 1 mole sodium carbonate to 1 mole magnesium carbonate. So that cancels out. So now that we have moles of magnesium carbonate, we need to convert to mass, because that's our theoretical yield, potentially. And so the molar mass is 84.32 grams of magnesium carbonate per mole of magnesium carbonate. So that cancels out. And if we plug all of these, the whole long thing, so 8 divided by 1,000 multiplied by 0.02, multiplied by 1, multiplied by 84.32 should give us to 1 sig fig 0.01 grams of magnesium carbonate. So let's look at our two possible yields. we recognize that this one is a smaller amount, which comes from the sodium carbonate. So this means the answer question part C, Na2CO3 is the limiting reagent. And that means that we have part D answered. The theoretical yield is 0.01 grams of magnesium carbonate. All right, so there we have it, a very long and complicated, seemingly complicated theoretical yield calculation. To do these, we have to do two sets of identical calculations starting with each of our reactants every time to figure out how much product they'll form. The one that forms the smaller amount of product is going to be our limiting reagent, and that smaller amount of product is our theoretical yield, often written in terms of grams, but it can be in other quantities as well. All right, I hope that all makes sense. It's a lot of stoichiometry calculation, so this continues to build on what we learned previously about stoichiometry, and it just takes it a little step further by using two different reagents with different starting amounts. All right, in our next video, we're going to look at percent yield and how this follows from the theoretical yield. We'll see you then. Bye.